The last lecture for our Trig unit. This is a review lecture. We're going to be reviewing some topics we've learned this week and also demonstrate a more sophisticated problem or two. How are you doing today, Mr. Stern?
Doing well, thanks. And you?
It's a great day to do some trigonometry.
It's always a great day to do trig.
Alright, you're going to need to open your packet up to page 52. We will be completing page 52 and 53 during this lecture. We'll give you opportunities to pause and try things yourself, and then you could check it using our solution. Alright, so number 3 I really like because it says the sides of a rhombus all have length 9, meaning we have to remember the properties of a rhombus. So I'm going to use my handy dandy rhombus maker and go ahead and mark all 4 congruent sides to be 9. And then I'm curious, why would we have a problem about a rhombus in our right triangle unit?
If we draw the diagonals of a rhombus, well, I believe that they're perpendicular.
Oh, so perpendicular diagonals make a right angle, and therefore we have 4 right triangles. And it says one of the diagonals forms a 16-degree angle with one of the sides. Now I'm just going to choose what looks like the smaller of the angles, but really it doesn't matter. So I'm going to label this angle as 16 and remind ourselves that that angle is a right angle. Then it wants to know what is the length of the longer diagonal of the rhombus. If you're worried about choosing the wrong one, you could always just find the lengths of both diagonals and then go from there. But say I want to find this diagonal first. I'm going to call that x, and then relative to my angle, what 2 sides do I have?
Opposite and hypotenuse.
So let's go ahead and write sine. Now if you think you know what you're doing, go ahead and press pause and try to finish this problem yourself. Alright, so sine 16 equals x over 9. So I'm going to have to multiply the sine of 16 by 9. So I'm going to go to my calculator. 9 sine 16. We get the missing leg to be about 2.5. Now if x is 2.5, what's the length of the entire diagonal?
Double it, 5.
Good, so the one diagonal is 5. I'm going to go ahead and call this other side y and write a trig ratio to solve for y.
Cosine, adjacent to hypotenuse.
Great, so we'll say cosine of 16 is adjacent y over hypotenuse 9. Go to your calculator and hit 9 cosine
16.
And we get our answer to be about 8.7. Now, if we double that, the entire diagonal would be
17.3 or 17.4, depending on your rounding.
So which is the longer one?
17.4.
Oh, how did you guess? Nice job. Alright, now let's take a look at the next problem. This is a more sophisticated problem. This is the reason we decided to make this a lecture. It says Dan needs to figure out the height of a mountain, but he's not exactly sure how far away he is. So obviously we're going to have a right triangle. That's our mountain. Well, I guess I could make it fancier. Here's the mountain. Here's the snow. Here's the hiker. Yes, and he's still yodeling.
You're not going to yodel for us this time?
Yodel-a-hee-hoo. Alright, there's the height. We've already done problems like this before. Alright, from his first position, Dan finds the angle of elevation to the top to be about 46 degrees. So I'm going to say that this is his first position. From here to the top, he finds this angle to be 46. He then says that he moves 2 miles back from the mountain, and that changes the angle to be 31. I'm going to change colors. Now this angle is smaller, it's 31 degrees. And it says, what's the height of the mountain in feet? So we do have some units issues that we're going to take care of at the end, because we have a distance in miles and we want our answer in feet. Let's not worry about that quite yet. We're interested in the height of the mountain, so let's make sure we make the height one of our variables. But then we also don't have the distance from here to here. So let's go ahead and call this y. And we're going to set up 2 trig proportions that we're going to use to solve. So for the first one, let's use the 46-degree angle.
Sure.
What can we set up, Mr. Stern?
I'd like to use sine or cosine, but they both require the hypotenuse.
Yeah.
So it has to be tangent.
Good. So tan 46 is equal to what?
X over y.
Oh, we have two variables, so we definitely can't solve it yet. But I can make it a bit more friendly and go ahead and multiply each side by y. And now I have that y times the tangent of 46 is equal to x. Still can't solve it. I'm going to hang on to that and go ahead and go to my next angle. So now, Mr. Stern, relative to the 31-degree angle, what two sides do I have?
Opposite and adjacent again.
Yeah.
The tangent of 31
Tan 31
equals x over the quantity 2 plus y.
Yes, this whole distance here is the entire adjacent side. We have to add those two lengths together to get 2 plus y. Now I'm going to go ahead and multiply each side by 2 plus y, just like I did in the other one, to make my equations a little nicer. So now I have 2 plus y times the tangent of 31 is equal to x. Now we know from algebra if they're both equal to x, then they're both equal to each other. Alright, so I'm going to set them equal, but I'd like to go ahead and find some decimal equivalents for our tangent so that we can get the tans out of there. So I'm going to go to my calculator and find tan 46, and I'm going to round that to 1.36. So I'm going to write 1.36y equals x. Notice I went ahead and switched the order. I put y. What are you trying to say, Mr. Stern?
What did you get for a tangent of 46?
I got 1.036. Oh, thank you for catching my mistake.
No problem.
Yes. Jump right in there. Alright. Now over here I'm going to do the same thing. I'm going to do the tangent of 31. And when I do that, I'm going to round this to 0.601. So now I have 0.601 times 2 plus y is x. Now I'm going to go ahead and set them equal to each other. 1.036y equals 0.601 times quantity 2 plus y. Distribute, simplify each side, so this side will stay the same. Over here, I get 1.202. How did I do that so fast? Plus 601y. Mr. Stern, what should I do next?
Let's subtract 0.601y from both sides.
Yeah, we need to gather our variables. So minus 601y minus 601y, and we get
0.435y.
0.435y equals
1.202.
1.202. Now go ahead and divide. And we get
2.763. But what's our unit?
Well, our units are miles currently, and we want to get eventually to feet. But we're also not quite done with the problem because we really want x.
Oh.
So let's find x, and then let's worry about units last.
Okay.
So I have an equation that relates x and y, and it looks like this is the simplest one right here. So I'm going to take my y value of 2.73 and plug that in.
2.763.
Thank you. 2.763 times 1.036.
And we get about 2.863.
Good. And that's going to be miles. Now, depending on where you round, your answers might be off by a hundredth or a thousandth. Alright, so now we want to go to feet. Mr. Stern, how many feet are in a mile?
5,280.
Alright, so if I want to say 2.863 miles, and I want to go from miles to feet, I know I have to multiply. So what is 2.863 times 5,280?
15,115 feet.
And once again, depending on where you rounded, your answers might vary a bit, but as long as you show work, we'll be able to figure out what you got. Wow, that was quite the problem.
It was.
All right. Let's go ahead and look to page 53. And we will get you set up here, and then we'll have remind you guys to pause. It says the Leaning Tower of Pisa was approximately 182 feet tall from the top to bottom when it was built. But as we all know, the Leaning Tower of Pisa is not leaning. Now, I'm going to draw it a little more leaning than it is, so we can exaggerate it, so that you realize that that's the hypotenuse. And it says if an object is dropped from the top, it's going to go straight down, right? Making our right angle, and this will be with the ground. It will land 14 feet from the base, and we know that it was 182 feet when it was first built. And it wants to know the angle that it leans. So I'm going to make that x degrees, which we have over here too. Alright, go ahead and press pause and finish it up. Alright, to solve for x, what do I need to do?
Cosine adjacent over hypotenuse.
So the cosine of x is going to be equal to 14 over 182. So in your calculator, you have to go cosine -1 or second cosine. 14 divide 182. And I get second cosine 14 divide 182. Enter. And we get
about 85.6.
85.6. And if we round, that's about 87 degrees. Typically, I always tell my students to round to the nearest whole degree. What do you do, Mr. Stern?
Rounding to the nearest whole degree is perfectly fine,
Mm-hmm.
but I think it would be 86 degrees.
Oh, man, the cold medicine's going in my head, isn't it? That's what I'll blame. Thank you, Mr. Stern,
No
for catching
problem.
my mistakes. Alright, imagine you're walking towards a lighthouse which is 80 feet tall. And what will the angle of elevation to the top of the lighthouse be when you're 300 feet away? So say that's 300. You want the angle of elevation, which will be right here. Go ahead and press pause and try to figure this out yourself. Alright, coming back, this should be a tangent of our x angle equals 80 over 300. Go to your calculator. Second tan 80 divided by 300, and we get 14.9, which
roughly
we could
15 degrees.
Exactly. Nice. Then it wants how far from the lighthouse will you be when the angle is 50. So the lighthouse's height doesn't change, and it says that the angle is 50 and wants to know how far away you are. We'll call that y.
We're still going to use the same trig ratio, so another tangent problem.
Nice. Tan 50 is opposite 80 over y.
Then we get to do our handy dandy exchange.
Our exchange, we switch those two. So we get y is 80 divided by the tan of 50. Now I'll go to my calculator. 80 divided by tan 50. And I get 67.1. And it says, looks like we're in feet. Alright, and looks like our last setup here. A ladder reaches a window 40 feet above the ground and makes a 55-degree angle with the ground. What is the length of the ladder? I'm going to redraw it. We know that's 40 feet above ground. We don't know the length of the ladder, but we do know that it makes a 55-degree angle. Which trig function should I use?
Opposite over hypotenuse, sine.
Alright, press pause if you want to know this yourself. Alright, you should have set up sine 55 equals 40 over x. Now we can do our switch and say that x is 40 over the sine of 55. Mr. Stern, what do you get?
I get 48.83.
And it looks like we are in feet. That's one heck of a ladder.
Yeah.
If the ladder were moved so that it reaches 46 feet above ground, so our height is now 46, what is the new angle? So we're going to use our ladder here. Can we round that to 49?
Sure.
For fun. Our ladders, which we found in part A, we're rounding to 49. And it wants to know the new angle with the ground. Which trig function should we use, Mr. Stern?
Still opposite over hypotenuse,
exactly.
So it's still sine.
So the sine of x is equal to opposite 46 over 49. I'm going to have to do inverse trig, second sine, 46 divide 49. And what do we get, Mr. Stern?
We get 69.8 degrees.
Let's round that to a healthy 70 degrees.
Sure.
Well, looks like I knew how to round that time. Sorry. To the nearest tenth of a foot. How far must the bottom of the ladder be moved to form the new angle? So, we have to know the bottom of this triangle and the bottom of that triangle. What do you think, Mr. Stern?
In order to get the bottom of the triangle, we could use the Pythagorean theorem.
We could.
We could use cosine, or we could even use tangent.
All right, well, what do you want to do?
So many choices. It's like a smorgasbord over here.
Well, you choose, Mr. Stern.
Let's go back up to part A.
All right.
And can we label that bottom with a new variable?
Sure. What variable would you like?
Y sounds good.
All right, so we'll call that one y.
And let's use cosine.
Okay.
So the cosine of 55 degrees equals adjacent over hypotenuse. That's y over 40.
Well, our hypotenuse we found to be 49.
Oh, thank you.
Hey, no problem. It's what I'm here for. So we want to find the distance the bottom of the ladder was originally by multiplying 49 by the cosine of 55. Woo! 49 times the cosine of 55. And we get that the original distance was about 28. Now, how would you like to come up with the new distance when the ladder got moved?
Let's use tangent this time.
All right.
So
I'm going to call that z.
We've already determined that angle, 70 degrees.
We did.
Tangent of 70
All right.
equals opposite over adjacent.
So 46 over z.
Yes.
Let's do our handy-dandy exchange.
So we have 46 divided by tangent of 70. And we get about 16.7.
All right. Do you mind rounding that to 17?
Go ahead.
I like rounding. All right. So then it says, how far must the bottom of the ladder be moved? So how far did it move?
It moved from 28 to 17. That would make 11.
Great. A little subtraction, and we get 11.
But we should mention that we did a lot of rounding in that problem.
Yeah,
and
we
so
did.
answers will vary.
Yeah, well, I was a fan of rounding once I started getting them right. All right, you guys, if you have any questions on this, just jot a note on the side in the margins of your packet on page 52 and 53 so that you remember to ask us in class tomorrow. Have a nice night.
Goodbye.